Okay, in this lecture, we're going to talk about hypothesis test for one population mean. And this section is actually going to help us with your midterm. So you're going to hear a lot of terminologies, a lot of jargons that are going to help you make sense of the midterm questions, which have quite a few hypothesis tests on them. So let's actually proceed with this. First of all, I have defined what a hypothesis is. These are all definitions that I pretty much made up, but they are fairly accurate. What I try to do is I try to make this as simple as possible, but yet accurate, so it's not too wordy, so you can actually remember this stuff. So again, this hypothesis is going to be a conjecture or an assertion or a claim, if you will, that is made about the value or values of the population parameters. And here I have a couple of examples I made up. Okay. Now, my first example is kind of sensible, whereas my second example is not so sensible, right? My first example reads that the average rent, note in both cases, by the way, I'm talking about the average. So mu is what we're doing here. This is the population average. That the average rent for a one-bedroom apartment in that zip code is $1,500 a month. I guess being in San Diego, that is sort of reasonable and sensible. The second example is not so reasonable. And it reads that the average community college student earns about $120,000 a year. That one is a hard sell. I know that, but I'm doing this for a reason. I know it's not realistic, but I'm doing it for a reason. Now, when it comes to hypothesis tests, every hypothesis actually has two statements in it. So it's made up of two parts. It's made up of the null and it's made up of the alternative hypothesis. Okay. So, first, the null hypothesis. The null hypothesis is the hypothesis that we want to test, and usually it's referred to as the status quo hypothesis. So, for example, in my $120,000 a year, my statement is actually the null hypothesis. That's the status quo, unless somebody comes and wants to challenge that. You see how that could be status quo? So, things are the way they are before somebody comes and challenges them. Now, symbolically we use H with a subscript 0 looks like, but that's actually the null symbol. Like I have an example here. And this is like 30 degrees. This is the degree symbol, the null symbol. So it's not quite a 0. It's like an open circle, tiny circle, the null sign, if you will. The alternative hypothesis is actually the hypothesis that is a complement of the null. Okay, I'm actually sorry about that jump. I'm up here. The alternative hypothesis is what the researcher is actually trying to work off of. So this research hypothesis is trying to, if you will, disprove that the status quo is actually true. Okay, so it's trying to negate it, if you will, or reject it. That means something has actually changed. The status quo no longer holds. And in our case, that means the value, the parameter, actually has changed. It's no longer what it used to be. Now, symbolically, we have different subscripts here. Little a, cap A, both of those means alternative. Subscript R here means research. And for those that think of the subscript on the null as 0, well, they can think of this as a 1, which it is, a 1 here. Okay? Now, keep in mind the null and alternative are complementary events. So they're always going to be complement of each other. Now, what is a hypothesis test? A hypothesis test is going to be a set of procedures that eventually will lead to a rejection or non-rejection of the status quo. Okay. Now here I have some examples of null and alternative statements. The first example reads, The null says the new vaccine is not effective, and the research wants to show that the vaccine is effective. Okay. The null is, remember, the status quo here. The status quo means, the vaccine is not going to do anything. So things are the way they were before this vaccine was proposed. The other example I have is that the average community college student makes $120,000 a year. And the research here, the alternative, I can state it that the average student does not make $120,000 a year. And they become exact complements. Now, in this chapter 4 we are actually interested in testing hypotheses about the mean of the random variable x. Remember, the unknown of the center of the distribution of x. So there are actually 3 forms of the alternative here. The null hypothesis reads mu is less than or equal to some hypothesized value. Okay, that's what this mu subscript 0 is. If we call that the hypothesized value of the mean. Okay. And the alternative is going to be the negation of that. Again, complement of less than or equal to is greater than. Complement of equal is not equal. Complement of greater than or equal is less than. Now, the alternative that has greater than in it, we refer to that as a right tail test. If the alternative does not equal to, this is referred to as a two-tail test. And if it's less than some hypothesized value, then we call that a left tail test. That's just to classify or categorize the hypothesis test. Okay. Now, again, I have here mu sub 0, if you will, but it's really not 0. I have the correct verbiage here. We call that mu naught. Mu naught, that means this symbol down here. That is the hypothesized value. So my $120,000 for community college students, that's mu naught. Okay. Now we're always going to take the null to be mu equal to mu naught, by the way. But if you really want to be technically true, you should, if the alternative is greater than, make sure that's less than or equal. So for like midterm and your homework, maybe follow this guideline in here. But in practice, what we do is we always assume the null says the mean is equal to the hypothesized value. Okay. And when we go to Minitab, that's what we're going to put into Minitab. Now, here I have something that you may wonder, well, how do I know which of those I use? Is it going to be less than, greater than, or not equal to? One thing, by the way, that you want to note here right off the bat. If you look at the alternative in all 3 cases, the alternative is not allowed to have equal sign. So that's a big hint. When you try to set up these hypotheses again on your exams or in your homework or in your research, do not put equal sign on the alternative. The alternative will never have equal sign. And by contrast, the null will always have equal sign in it. Okay, if you look at all 3 formations, every one of those have equal. Okay. And so there we have that one. Now, how do we know when it's less than, not equal, greater than? I have it here for you. We always look for these keywords. At least, at most, no different or no difference, no more, exceeds, any one of these words that somehow turn out to be an inequality as we write them. So, now what's the logic behind this? What are we going to do? And here I have it in one paragraph, the logic of hypothesis test. And I guess it's common sense. What we want to do is we want to choose a sample, a random sample from a population. The null says the mean is whatever. And we get a sample from the population. And we're going to compare the sample mean to the hypothesized value of the mean. And we're going to see how far apart, how far away they are from one another. The closer the two are together, that means the lesser of an evidence we have against the null. The farther they are apart, the stronger the evidence against the null. Okay, so that's pretty much the logic of how we're going to do this. Okay, so, and I have written for you that in one paragraph. You can read that paragraph, but pretty much what I mentioned is the logic behind it. Okay, now, what is the mathematical engine behind a hypothesis test, right? Everything we do must be based on some kind of mathematical construct or structure. So, in the case of hypothesis tests, the mathematics behind it is based on proof by contradiction. Now, I'm sure you probably heard of it, and you may have proved something by contradiction in your lifetime, but here I have a simple example of proof by contradiction. So, in this example, I have it use proof by contradiction to show that 2 plus 1 equals 6 is an incorrect statement. Right, 2 plus 1 equals 6. Notice that. I know that's incorrect. That's not a typo, but that's what we want to prove. So, how do we prove by contradiction? Well, in this line of proof, we always assume the hypothesis of that statement is true. So, in other words, we're going to assume, okay, well, 2 plus 1 equals 6. I'm going to say that is true, although we know it's not. But we're going to say, sure, it's true. But then if it's true, isn't it true? If it's true, isn't it true that if I have, let's say, 2 apples, and I add 1 apple to it, I should get 6 apples, don't I? If that hypothesis is true, if that statement was true. So you actually look at these counts. 2 apples plus 1 apple. It looks like in my hand or my hands, I'm holding 3 apples, not 6, do I? So we have reached a contradiction. And the proof is complete by contradiction. A very simple proof, just to get the idea across. So hopefully you're okay with that. Now, a more profound example is going to be this one. Our judicial system, folks, is actually based on proof by contradiction, right? We all know that. Any defendant that walks into a courtroom is presumed to be innocent, true, unless proven guilty. So, this would be the same as 2 plus 1 equals 6. Even though there are videos, there's overwhelming evidence, witnesses, and so on and so forth against the defendant. But nonetheless, the moment the defendant walks into that courtroom, the assumption is that of innocence. And that's the fundamental basis of proof by contradiction. So, here I have the null hypothesis is that the defendant is innocent, meaning not guilty. The alternative must be complement of that, right? That it is guilty. It doesn't say may be guilty, but it has to be complement in this case. So, in this line of proof again, we always assume the null is true. Always, regardless of how ridiculous it may sound. And that kind of goes to my community college example. The student on average make $120,000. No matter how ridiculous it sounds, we're going to say, okay, that sounds good. Actually, that would be nice if they did. So, now, the alternative here is that reads defendant is guilty. And if you remember, or if you recall, it is up to the prosecution, right, to gather evidence against the null. So in our line of work, it's exactly the same thing. It's up to you and I to collect data, information, to negate the null, possibly reject the null hypothesis. Okay, so now this is actually something interesting. I have a table here. I put the table here together. Okay, in this table, the top line reads the true state of nature about the null. the null is true or false. Now, what do we mean by true state of nature? Let's say they handcuff me, they take me downtown, and I'm accused of a crime. The true state of nature means this: only I know whether I have committed a crime or not. True? You guys don't know that, but I know. So that's what we mean by true state of nature. It means things are truly the way they are. So the null is true or the null is false. So going back to our courtroom example, the true state of nature about the defendant, true means the person that's sitting there is truly, truly, truly innocent. Or the other side of that coin, the person that's sitting there is truly guilty, although the system calls him innocent or her. But in actuality, that person is guilty. And then to the left of this table, I have the decision that the jury renders when the trial concludes. The jury comes out and the decision is to reject the null hypothesis, that is the hypothesis of innocence. Or they can come out and render the other decision. They say accept the null hypothesis, the hypothesis of innocence. So in other words, reject the null means they found the person guilty. Accept the null, they found the person innocent. Now in this 2x2 contingency table, I have check marks in two locations here. These in terms of whether the correct decision is made or not. So if you look at this check mark that it's right now, the null hypothesis is false. False, truly false. That means the person is guilty. The jury comes out and rejects the hypothesis of innocence. So in that cell, the correct decision is made. The person is put in jail, and rightly so. In this lower left position is another check. Another correct decision is made here. This time, null is true. That individual is innocent. The jury comes out and accepts the hypothesis of innocence. So the person is ultimately set free, and rightly so again. True? So the correct decisions are made in those two positions, those two cells. Now, look at the one in here. Type 1 error. A type 1 error is committed when the null is true. The person is innocent, but the jury comes out and rejects the assumption of innocence. In other words, they find the person guilty. So in this cell, an error is committed. We're going to call that a type 1 error. The other kind of error is in this location, type 2 error. That's when the null is false. That means this person is truly, truly guilty. The null is false. But the jury comes and accepts the hypothesis of innocence. They say, no, he or she is innocent. We just didn't have enough evidence to convict them. Okay, so both errors are bad, by the way, here. Type 1 error, for example, in my case, myself. Null is true. I'm truly innocent. They say I'm guilty. I'm not happy about it. And here in type 2 error, that's when null is false. I know I'm guilty, but I had this great attorney that can get me off the hook. And the jury comes out and says, there wasn't enough evidence to convict them. So I'm set free. Now, I'm sure the society is not going to be happy about it. So, now, I went ahead and wrote these two types of errors. Okay. Now, in this course, by the way, everyone, we're going to be focused on a type 1 error. We acknowledge the type 2 error, but we're not going to do mathematical work. And we're not going to do anything in Minitab about the type 2 error. Our focus will be primarily in type 1 error. So there you have it. A type 2 error is accepting the null when in fact it's false. Now this table is going to help you, by the way, when you do your, again, midterm. Try to use this table in your work, and it's going to make answering those questions a heck of a lot easier. Now, when it comes to probability of committing these two types of error, probability of committing a type 1 error is alpha. And this is, by the way, exactly the same alpha that we encountered that we saw when we talked about confidence interval. Remember, in that segment on confidence interval, we called alpha the uncertainty level of a confidence interval. So alpha was a bad thing there, uncertainty. It's a worse thing here. So in both cases, alpha does not play a good role. And probability of a type 2 error, that's going to be beta. Okay, so again, alpha and beta are probabilities. Being probabilities, they're each between 0 and 1. Now, actually here, I don't have it in chapter 8. We saw this in chapter 4 earlier, actually, in the section of chapter 4 is where we saw this. Remember the earlier lecture prior to this one, before the margin of error. So we saw alpha in chapter 4, and we called it the uncertainty level of the confidence interval in that segment. Now, here are the AKAs for alpha. Alpha is called probability of a type 1 error when it comes to hypothesis test. Alpha is called the size of our test. And alpha, it's the stated significance level of the test. So all of those are the role alpha plays. And I want to emphasize alpha is a bad thing. Now, we don't want too much of a bad thing, right? So being a bad thing, we want to minimize alpha. Now, when it comes to beta, beta is not so good either. Beta is a bad thing also, because both of those involve committing an error. Now, beta is probability of a type 2 error. And the typical values, by the way, that we're going to use for alpha are 10%, 5%, 1%. Now, as far as since we commit both kind of errors, we would like to minimize both kind of errors. I'm not happy when I'm in jail and I'm innocent. I'm sure the society is not at ease when a guilty person is set free. So we want to minimize both kind of errors, because somebody is going to suffer as a consequence. So it turns out mathematically, again, unfortunately, alpha, beta are inversely proportional to one another. That means when you try to do good on one end, you're not doing so good on the other end. When you try to minimize, shrink alpha, beta on the other side is increasing, getting bigger, bigger, bigger. It's growing. If you try to grow alpha, you're shrinking beta. You try to grow beta, you're shrinking alpha. So how can we actually simultaneously reduce both of them? The only way is to boost our sample size. And that's the hope here, that we can increase our sample size. Everything good comes out of large sample sizes, folks. Everything turns out much better. So now here are an example of a type 1, type 2 errors. Again, in your homework and possibly on the midterm, there are questions that ask you state what is a type 1 or a type 2 error in context of the word problem. So this is what's going to help you. So in our court example, what is a type 1 error? Remember, reject and null when it's true. So that's when an innocent person is found guilty. Reject and null found them guilty, and the decision found them guilty, and the true state of nature was the person was innocent. And what would a type 2 error be? Is when the guilty person is set free. Okay. And we'll see another example in a minute where we have to determine what is a type 1, type 2 error. Now, when we talk about statistical significance, anytime we reject a null hypothesis, we call the result statistically significant. What that means in a nutshell is this. With statistical significance means a null hypothesis was rejected. The status quo no longer holds. Okay? So that's what we say. The test results are statistically significant for the given alpha. Okay? And let's take a look at this example. This is actually an interesting exercise. I got this from another textbook. This exercise has to do with the early onset of dementia. And you can kind of read the introductory paragraph to this. But here are the things we want to do in this exercise, okay? We want to determine the null, the alternative, and classify this as a two-tail, left tail, or right tail. And we do more with this also. In fact, we'll determine what is a type 1, type 2 error, and so on. So, first of all, let's take a look at the statement of the problem here. By the way, let me hide this from you for a moment. Okay, so the statement of the problem here is as follows. Reading this, going right down to here. A hypothesis test is to be performed to decide whether the mean, that's mu, age at diagnosis of all people. You see how inferential that those words are. When we talk about all people or all measurements, all possible outcomes, we're talking about the population. So that's what the mean is, the population mean. So it's going to be mu. So we want to decide whether mu with early onset of dementia is the mean age is less than 55. So that's what we want to know, whether it's less than 55. So the fact that it's less than makes this the alternative. So what is the null going to do? The role that null is going to play here. Null is going to say the average is indeed 55. Okay? Or, to be more accurate, it's going to be greater than or equal 55. The alternative here, the mean is less than 55. Okay, because notice that's what they want to decide, whether the mean is less than 55. So because it's less than, then this is a left tail test of hypothesis. So that was pretty easy. Now, let's take a look at this part. Actually, sorry, there you go. It's that same exercise that we just looked at a moment ago. We want to know what is a type 1 error, what is a type 2 error, and what is a correct decision. And once we do, we're going to look at this next segment, part D and E. So ignore parts D and E for now. Let's just focus on A, B, C. Type 1, type 2 error, and the correct decision. So if you have that 2x2 table and kind of written down somewhere, you can scroll up and get that table and see if you can maybe pause the video, actually pause the lecture and see if you can figure out what is a type 1, type 2 and correct decisions, what these are. And then come back, watch the rest of the video. So here's actually the answer to part A. Remember, type 1 error is rejecting a null when it's true. So, and the null hypothesis says mu is 55. If we reject it and it's in fact 55, that's what the type 1 is. So, I've written a type 1 error is if mu is indeed 55, but the result of the sampling lead to the conclusion that it's actually not 55. In this case, the alternative said less than. What is a type 2 error? Remember, type 2 error was accepting the null when in fact it's false. When null is false, means alternative is true, right? So in this case, if mu is less than 55, because the null is false, but the result of the sampling fail to that conclusion. In other words, again, we do not reject the null when in fact it was false. And we should have done that. So what is the correct decision here? The correct decision would be the 2 check marks on the table. When the null is true and the jury comes out and says, yeah, accept it. Or when it's false and the jury comes says reject it. And here are the correct decisions. If mu is indeed 55, and the result of the sample don't lead to the rejection of that, so null is true, we don't reject it. Or the alternative is true, and the result conclude that. That means the null is false and we don't accept it. In part D now, let me go back up here. So I have it boxed in for you. The question reads, now suppose the result of carrying out the hypothesis led to non-rejection. Led to non-rejection means, okay, the average age at the early onset is 55 years. Suppose this is what the researchers came out with. See, the result of carrying out the hypothesis led to that conclusion. Classify the conclusion now by error type or as correct decision. If in fact the mean age, that's the true state of nature I talked about earlier. If in fact the mean age at diagnosis of all people with early onset of dementia in part D is 55. So if in fact the age is 55 and we did not reject it, well, it's 55. In fact, it's 55. The sample didn't reject it. Looks like that was a correct decision, wasn't it? Look at part E. The result of sample came out, says mu is 55. But it's indeed less than 55, means the alternative should have actually prevailed, and it didn't. So, it looks like we accepted a null when in fact it was false, huh? Accepting a false null is a type 2 error. And there you have it in part D. The result didn't reject the null. If mean is 55, then this is a correct decision. And in part E, the result, we did not reject the null, just like in part D. Remember, the conclusion was they did not reject the null. But the truth is that they should have. Okay, so for this one, we committed a type 2 error. Okay. So again, you're going to be asked to do this kind of work in your, I believe, homework, and I strongly believe on your midterm. So hopefully this example and this whole lecture on this segment is now going to help you do what I'm hoping you're going to do on the midterm. So we're done with this segment. Next lecture, we're going to actually run a procedure. I'm going to see how we're going to test this hypothesis. So we're done with this segment. Let's take a break.